and obviously you have to consider that you do not have the fatigue. The fatigue limit concept is not going to work for your component. So this is the mechanics. So these are called intrusion and extrusions, okay, which form at the surface and they result in a crack. So the question is, technical question is that when can you call this small atomic scale thing a crack? So there has been a lot of research on this, and people have decided to define something which is called short crack and then crack. So macroscopic crack is called crack. Crack which are smaller in sizes are called short crack, and we will not discuss the limits of those and what is the value when we say that that is a short crack or not. But these cracks behavior is completely different from the crack which we study in the macroscopic level. Okay. So we have discussed in fractography previously that the material, so for example in ductile material you have dimples, and you know why dimple form. In brittle material we see river patterns and tongues, so we know why that forms. In fatigue, the broken specimen will show striations, okay, and striations are visible only in a scanning electron microscopy, not by the naked eye. The naked eye signature of fatigue is called beach marks, but beach marks are not necessarily available in all kind of fatigue fractured specimens or components. Also striations are not visible in all the fatigue failures because striations can be very small, but striations do give you some information about what kind of material deformation you have had in the specimen. So now imagine a crack, and I will draw a crack like this, and you will realize in some time that why it is so. So imagine that this is my initial crack, okay. Although it looks, we have not discussed this kind of crack before, but just hold on with me and you will realize why it looks like this. So what happens is that I apply a stress in the tension direction, and when I do that, obviously this part is not connected with the material, right. So that will open up very easily, so it will look like this, and this part which is connected to the material will not open up. So it looks like a hinge now, right, and here you will have shear stresses, right, and we know that shear stresses usually happens at an angle close to 45 degrees. So you will have shearing happening in this direction, and therefore I have this kind of opening here, right. The shape which is like this, if you see the plastic zone, so we have discussed plastic zone in fracture mechanics, and in reality that plastic zone at a crack tip, so we drew a plastic zone which was like a circle, but in reality it is not like a circle, in reality it looks like a butterfly like this, okay, and because of shearing. So that kind of shape also is formed here because of shearing, and so the material is deforming in that direction, right. Because of this there can be a crack growth if the material, so if the stress is higher than what material can take, or the strain is higher than what material can take, so the crack will grow, right, or not if the stress is not higher or if the damage is not higher. Then, so this happened in the tension part, then what you do is you apply compression, right, because that is the, so in the stress cycle you have tension till here and then you unload till here and then you apply compression, right. So this is the part where you apply compression. So in compression what will happen, but before compression, so after having this, if so After once shearing starts and you still are in loading in tension condition, then what will happen is that this crack will become blunt, right. So, this part which was like this, because now you are applying tension, it will just open up these parts and it will look like this blunt crack. Blunt crack, there will be large strain here, the material can propagate by certain amount or not, and then you apply compression in the reverse cycle. So, then this blunt crack becomes sharp again. Okay. So, it becomes sharp again, it gets closed, right, and then the same thing is repeated over and over again, and because of this damage the crack can propagate. So, what is happening is that because of this shear band, the crack takes this kind of form, right, then it propagates and this part is left there, and this is why you see these parts. Okay. These parts are the previous shearing which has happened, and so the crack has moved from this part to that part in each cycle. Okay. So, this is one cycle, this is another cycle, right, and this is in 2 dimension. Imagine this thing in 3 dimension. And in 3 dimension, if I have a microstructure like this and the crack has propagated, then these things in 3 dimensions will look like that, right. So, these things in 3 dimension will look like lines, right. The crack has propagated, so in each cycle, and these are the lines which are formed because of the shear band opening, and these lines are striations. Okay. So, you see that striations are defining how many number of cycles have been given to the material, right. So, they give you a lot of information about the number of cycles you have had, but the problem is that if the number of so if you have a very high frequency of load application, right, and crack is still growing, then you may have a situation something like, so you have one cycle and then the crack propagates, another cycle is just very close, very close to each other. Okay. So, in the microstructure what you will have is that these lines will be very close to each other, so close sometimes that you cannot differentiate them even by the scanning electron microscope, and therefore, sometimes you may not see striation. It does not mean that the material has not failed in fatigue. Okay. So, the presence of a striation in the microstructure confirms that the material has gone through fatigue, but the absence of a striation does not confirm that the material has not gone through fatigue. So, we will stop here today and we will discuss further on this in the next lecture. Thank you.